So I'll say it a third time. Good morning, everybody, and thanks for coming to this live edition of our ODE course. The first subject that I want to approach today is this question that I think Youssef, you wanted to ask. Can you please tell me what was the question that you wanted to ask about this equation?
I just had a question on how to start start solving it, but you answered my question by saying we need a coefficient of 1 for y prime just to make it easier.
Okay. All right. Well, then let's continue solving it anyway, because yeah, I think it's good to do more examples. So let's see. Share. Let's do the whiteboard share. All right. So the equation was y. So we arrived at y prime plus 2x over x squared plus 7 is equal to x to the fourth over x squared plus 7. And this 2x over x squared plus 7 is times y. Yeah. Yeah, good morning, everybody. So out of all these terms, now the most important one is the coefficient of y, so 2x over x squared plus 7. And we need to integrate it in order to find the integrating factor. So the integrating factor, it will be mu of x, this is the usual notation, is equal to e raised to the integral of 2x over x squared plus 7 dx. So can you please tell me the integral of 2x over x squared plus 7? Well, that's computed. So integral of 2x over x squared plus 7. In this integral, we are going to make the substitution. X squared plus 7 is equal to u. So we'll get so let's make a substitution. U is equal to x squared plus 7.
D is 2x.
So then du is just 2x dx, which is what we have on the numerator. So then this is the integral of du over u.
1 over u.
Which is natural log of absolute value of u plus a constant.
Six people.
Sorry? So now we can replace u back by x squared plus 7. So this is equal to natural log of absolute value of x squared plus 7 plus a constant. But x squared plus 7 is positive for any real number, so we end up with just natural log of x squared plus 7 plus the same constant. But then when we solve linear equations by this method of the integrating factor, there is no need to retain the constant. So any integrating factor will work. So then we should choose the simplest one, which involves just e raised to the natural log of x squared plus 7 without a constant. So, and right here, the constant is not needed here. So c is not needed. All right. So then this implies that mu of x is e to the power natural log of x squared plus 7, which is just x squared plus 7. So now we should multiply the equation again back by x squared plus 7, and we're back to the original equation, which I did not write on this slide. So we get, so multiply this equation by x squared plus 7. And we get x squared plus 7 times y prime plus 2xy is equal to x to the fourth. So we didn't really need to divide by x squared plus 7 and multiply again by it. So we could have skipped both steps if we had recognized from the beginning that the left-hand side of this equation, as it stands here now back to the original form, is d over dx of x squared plus 7 times y. So in order to do this, we need to be able to recognize when the coefficient of y is the derivative of the coefficient of y prime. But that's not always easy to recognize. So this is why we carry through this method. And in this case, we are guaranteed to always get the right integrating factor to multiply the equation by, so that the left-hand side becomes the derivative of a product. So it's not based on guessing in this case. So it's equal to x to the fourth. And now we integrate both sides. We get that x squared plus 7 times y is equal to the antiderivative of x to the fourth. which is of course x to the 5th over 5 plus a constant. So now we know that x squared plus 7 times y is equal to this. So y then is equal to x squared to the x to the 5th over 5 plus a constant divided by x squared plus 7. Right. So hopefully this settles this question. I mean, I know that you have already done it in the homework, but yeah, if you respect this logical order of steps and use the method of the integrating factor, then again, this is an algorithm that is guaranteed to lead to the correct solution. Now let's go back to the course slides. Let's see.
When we have
Yes.
an ordinary differential equation given to us, like the one we started,
Yeah.
is it typically going to be the denominator that's going to get canceled out every single time, or?
No, this is just a coincidence. It's because, so without us maybe noticing it, but of course some of us did notice it, the equation was already in the correct form. It did not actually need any integrating factor. So the original equation as written, x squared plus 7y prime plus 2xy is already integrable. There's no need to multiply it by any factor. So this is the reason why, when using the method of the integrating factor to make sure, what we did was we first divided by x squared plus 7, and then we multiplied back by x squared plus 7, which cancel out and give you 1. So, but in order to take advantage of this, actually all that you had to do is to recognize that 2x is the derivative of x squared plus 7. And then, so, okay, actually, let's try. I have tried a new function, so I think I can annotate on slides. Let's see. So let's see. So let's try on this slide, if I can. So this equation implies, looks like, it works. So this equation implies that already, it implies that d over dx of x squared plus 7 times y is equal to x to the 4th. So if we already saw it by looking at the equation, then there is no actual need to divide by x squared plus 7 and then multiply back by x squared plus 7 to make sure. But then we just need to be sure in the first place. So yeah, so this is how it works. Yeah, we did not did not need to carry out this division and multiplication, but usually this is not the case. Usually you have maybe to divide by something and multiply back by something else. So why doesn't it? Oh, probably because of the annotations. Thanks, Yusuf. Let's see. It's okay. Well, and this keeps the annotations from the previous page. That's not good. Let's okay, let's stop it and erase them. All right, so let's see. All right, so now I wanted to show you again the slides that probably I should have presented last time. And then I want to do a couple more examples. So a linear ODE is an equation that can be written as a linear operator t applied to y is equal to a function f, where t is the linear differential operator that defines the equation, and f is the source term, which can be 0 or can be non-zero. So if f is 0, the equation is called homogeneous. And let's see, maybe. So the equation is called homogeneous, and otherwise the equation is called inhomogeneous. Okay. And the order of the linear operator t is the same as the order of the equation by definition. And the order of t, also by definition, is the order of the highest order derivative that's present in the equation. So t is the sum of coefficients which can be functions of x times derivatives. And then the order of the highest derivative is called, the order of the highest derivative is also called the order of the operator. And it's also usual to, instead of for writing differential operators, there's actually a fourth notation for derivatives in addition to the three I presented earlier. So I mentioned the Leibniz notation, the prime notation, which I think is due to Euler, and dot notation, which is due to Newton. And there's also this capital D notation, which I think is more modern. And so this facilitates writing these linear operators in the abstract. So d to the 9, d to the 7, d squared. So we think of each higher order derivative as in some sense a power of the first order derivative. And by a power of the first order derivative, we mean the first order derivative applied that many times. So d to the 9 means d applied to d applied to d, whatever, 9 times. So this is also pretty convenient notation because one can do some computations with it. So one can try to even factor these operators, though that doesn't work the same way as for numbers because this operator does not commute with other functions. Does not commute with functions, I should say. So anyway, so this capital D notation is somewhat usual in writing linear operators. So, okay. Now, again, let's recall the definition of a linear transformation. So, well, our linear operators are linear transformations in this sense. So, T, I should have said, T of V1 plus V2 is equal to T of V1 plus T of V2 for any V1 and V2 in the vector space capital V. And T of alpha V is equal to alpha T of V for any V in the vector space capital V and for any scalar alpha. And for our equations, again, the usual scalars are either reals or complex. And now I want to say a couple of words about the vector space. What is the vector space V? I didn't mention it last time. So usually it's some vector space of differentiable functions. So Cn means the space of n times continuously differentiable functions. So functions that have n derivatives, and the function itself together with all of its n derivatives is continuous. So then in order for this operator to be well defined, well, we would like to have at least n derivatives. So, I mean, we would like the function here to which we apply the operator to have at least n derivatives. So this means that a good choice for the vector space is Cn, the space of n times continuously differentiable functions. And this takes values in C. By C, I mean just a space of continuous functions. And both Cn and C are vector spaces, and T is a linear operator between them. Okay, so a couple of more examples here. Probably we should solve some of them. So let's see, not all are equally easy to solve. So I just wanted to give them as examples. Y prime minus y is equal to 0 is a linear homogeneous equation, yeah, with constant coefficients. So I guess we can add to it that it is first order and autonomous. So and the linear operator that appears in the equation is the derivative minus 1, which can be written as d over dx minus 1, or could also have been written as capital D minus 1. So let's see. Maybe let's do that. So y double prime plus sine of x times y is equal to 1. Well, can you please tell me what sort of equation is it? It is.
You say what order?
It's second order. Very good. And what about autonomous versus non-autonomous? It's non-autonomous because it has the sine x. So this definitely makes it non-autonomous. And the linear operator is d squared over dx squared plus sine x, which can also be written as capital D squared plus sine x. But as we notice, it doesn't really have to be linear in x at all. I mean, sine is a very nonlinear function. The only thing that matters is that it's linear in y and its derivatives. And 1 here, indeed, on the right-hand side of the equation, is the source term for the equation. And y double prime minus sine y instead of sine of x times y equals 0 is a nonlinear equation, because when we have a nonlinearity involving y and its derivatives, that actually makes the equation nonlinear, whereas for x, the equation is still linear. So the set of solutions forms a vector space. I think I also presented it last time. So if Ly1 is equal to 0 and Ly2 is equal to 0, then Ly1 plus I2 is equal to Ly1 plus Ly2, which we know are both 0, and therefore their sum is 0. So whenever L of y1 is 0, which means y1 is a solution, and Ly2 is 0, this means that L of y1 plus y2 is also 0. So very briefly, I wanted to present the definition of a vector space. So it's a set with two operations. One is an internal operation, namely we can add vectors together. The other one is an external operation. We can multiply vectors by scalars. So vector addition has, and I see that I have actually managed to not write the property here. So it's associative. It has the zero element. So the zero vector is the neutral element for addition. Every vector has an opposite here. And I should have also written that it's commutative. So for any two vectors, v1 and v2, v1 plus v2 is equal to v2 plus v1. And here are the properties of multiplication with scalars. So all sorts of laws of distributivity that make computations manageable when multiplying by scalars. And if we have a smaller vector subspace, a smaller vector space within a bigger vector space, that's called a subspace. And the condition for a set to form a vector subspace are just two conditions, namely the sum of any two vectors from the subspace is in the subspace, and a scalar times the vector is in the subspace is also in the subspace. So if we know that there exists a surrounding vector space, then it's much easier to prove that a certain subset of it is a vector subspace. So an example here, R2 is a vector space with the usual addition and multiplication by scalars. And then this set, which is actually a line in the plane R2, is a vector subspace of it. So this is a line that passes through the origin, through 0. And what about an affine space? An affine space is a set of this form. So it doesn't actually make sense to define the addition of two elements of an affine space. So in general, you cannot add a point with another point. But what you can do is add a vector to a point. So maybe here I want to make a picture. Let's see. So if you have 2 points randomly in the plane somewhere, without considering them as vectors, so no regard to the distance from the origin, then you don't know what the sum of 2 points is. But if you take a point and apply a vector to it, then this will give you another point. So this is how an affine space behaves. It behaves like a vector space which forgot about the origin, which forgot about the 0 vector. So in an affine space, you cannot add 2 points because you don't know how far from the origin they are, because there is no specified origin in an affine space. But you can take a point in an affine space and add to it a vector from some specific vector space, like this one included here in the definition. So this is, I think, a characteristic example. The set of points of coordinates x, y, and R2 such that 2x plus y is equal to 1, not 0 as on the previous page. This is a line which does not go through the origin, so it is only an affine subspace of R2. We could give it a vector space structure, but it would not be useful, and we couldn't do it in a consistent way, probably. So the point can be chosen to be any point on the line. So here I'm referring to this definition and to A here in the definition. And the vector space is the vector space which, as a line, is parallel to this one, which is not a vector space. So in the plane, among all vectors that are parallel to, among all lines that are parallel to a given line, only one of them is a vector space. All the other ones, so in this case, it's probably this one. And all the other ones are affine spaces because they don't contain the 0 vector, And again, we could make them into vector spaces by specifying some arbitrary structure, but probably there is no good way, no standard way. So in a vector space, affine, so an affine space very often arises as a subspace of a vector space. So points, lines, etc., which do not necessarily go through the origin. If they go through the origin, then they're actually vector spaces. If they do not go through the origin, then they're only affine subspaces. Okay. So let's move on. Okay, let's see. Okay, so let's move on to the next page. Okay, so now let's consider again the difference between homogeneous ordinary differential equations and inhomogeneous ordinary differential equations. Last time I only presented the homogeneous ones and very briefly. So probably again I will say more about it in the course notes, hopefully next time. I mean, hopefully I'll present it next time. And so this is the important property that when the equation is homogeneous, solutions form a vector space, and the dimension of this vector space is equal to the order of the equation. So, for example, this is a second order equation, y double prime minus 4y is equal to 0, and we want to find a basis for the space of solutions. And we know that the space of solutions has dimension 2. And then, again, it suffices to come up with pretty much any two solutions. But then we need to make sure that they are linearly independent. So in this case, e to the 2x and e to the negative 2x are pretty natural choices for solutions, as we'll see not very long from now. If you have an equation of the form, so actually let me write this. So if you have an equation of the form y double prime minus 4y is equal to 0, so then actually, let's make it more general. If you have an equation of the form y double prime minus k squared y is equal to 0, then the solutions will be some combination of e to the kx and e to the minus kx. So let me write it like this, e to the kx and e to the negative kx. And if you replace minus k squared by plus k squared, then instead of e to the kx and e to the negative kx, then you'll end up with sine of kx and cosine of kx. So these are some pretty widespread equations. And so I think it is good to remember these formulas. So maybe again, I write them into the course. So y double prime plus k squared y is equal to 0 has solutions. Cosine of kx and sine of kx. All right, so what this means is that sine and cosine usually come in pairs. When you solve an equation with real coefficients, so like here 1 and k squared, or for the other equation 1 and minus k squared, then if one of your solutions is a sine, then you can expect the other solution or one of the other solutions to be a cosine. And exponentials also come in pairs like this, but it's more complicated. So yeah, so anyway, now what my other point was that it does not matter how we came up with these two solutions as long as they are linearly independent. So in this case, actually, I think that it's good to know these formulas. So y double prime minus k squared y and y double prime plus k squared y is equal to 0, what the solutions are. And then we use the Vronsky to check whether they are linearly independent or not. So this is a more general notion, which does not only apply to ordinary differential equations. So for any n functions, you can check whether they are linearly independent by computing the determinant of an n times n matrix. So what is that n by n matrix? On the first line, it's going to have y1 up to yn. And on the second line, y1 prime up to yn prime, and so on the next line. So because there are n lines, and we started with no derivative whatsoever, then the last one will have n minus 1 derivatives. So y1 with n minus 1 derivatives, and so on and so forth, up to yn with n minus 1 derivatives. All right, so this is a square matrix. It's an n by n matrix. And if we have two solutions, then that we want to check whether they're linearly independent or not, then it's a 2 by 2 matrix. And now, if the Vronsky is non-zero, then we can conclude the solutions are linearly independent. If the Vronsky is 0, then it's actually more complicated. There exists an example given by Peano that shows that, by the power of example, that shows that there are two functions whose Vronsky is always 0, but still they are linearly independent. So actually, it's a pretty straightforward example. So let me write here the Vronsky of the two functions x squared and x times absolute value of x actually is always 0, but the two functions are still linearly independent. So this example is due to Peano. All right, so in our case, we need to compute this determinant involving e to the 2x and e to the minus 2x and its derivatives. So now I have to erase everything in this. Okay, so the Vronsky in this case is pretty straightforward to compute. It's the determinant of a 2 by 2 matrix. And you, as you hopefully remember, but I'm going to write the formula anyway. So it's so the determinant of a 2 by 2 matrix is, so if the matrix is A, B, C, D, then its determinant is AD minus BC. All right, so in our case, it's going to be e to the 2x times minus 2e to the minus 2x, and then minus the product of the other two terms of the main diagonal. So both products are, actually one is minus 2 and the other one is 2. So, but there's a minus between them, so it all adds up to minus 4. And since the Wronskian is non-zero, these solutions form a basis for the space of solutions. And then any linear combinations of these two solutions are also solutions, and in general, the solution can be written as a constant times e to the 2x plus another constant times e to the minus 2x. So once you determine a basis, actually linear equations are very straightforward, but usually for more general equations, the functions in the basis are not easy to compute. So for example, let's go back a couple of pages. So for example, for this equation, y double prime plus sine of x times y is equal to 1, I think that the basis functions are pretty hard to compute. I mean, probably they have been computed, maybe there are even special functions that have their own names, but they are definitely not elementary functions. So now let's talk about inhomogeneous equations. So solutions to inhomogeneous equations form an affine space instead of a vector space. So this is the difference for homogeneous equations. The solutions form a vector space. For inhomogeneous equations, in general, actually always the solutions form an affine space. So as I mentioned, you take this vector space, whatever it is, a plane, a line, a point, and you shift it within the wider vector space so that it no longer passes through the origin. So in our case, what is the wider vector space? It's the space that I mentioned, Cn, the space of n times continuously differentiable functions. And what is the smaller vector space? The one that we move off the origin, it's the vector space of solutions. So solutions form a vector subspace of the big vector space of all differentiable functions with that many derivatives. And then once it's moved off the origin, it becomes an affine space. So what does this mean in practice? This means that the set of solutions is of the form some fixed solution A plus any solution of the associated homogeneous equation. So in particular, for inhomogeneous equations, the sum of two solutions is not necessarily a solution. And if you multiply a solution by a constant, then again, it's not a solution. So then for the equation y double prime minus 4y, let's consider it again now with an inhomogeneous term on the right-hand side. Then we have the same two solutions that we have already checked for the associated homogeneous equation. And then there are various methods, out of which my preferred method is the method of the undetermined coefficient that allow you to compute a particular solution to, it's not a solution of the associated homogeneous equation, it's a particular solution of the linear inhomogeneous equation. So then, okay, so let me actually cross this out. So it is a solution of the equation. So not of the associated homogeneous equation. So then, as I said, a couple of lines higher here. So every solution can be written as the sum of an individual solution of the equation and an element of this vector space, which is the vector space of solutions of the associated homogeneous equation. So what would have happened if we had chosen a different particular solution? Clearly, this is the easiest one to find, and it's the most simple because all the other solutions will also contain exponentials. So this is what the general solution is here. But what if we chose, instead of y0, we chose some other starting point? No, let's see. So what if we said y1 is equal to minus x over 2 plus 7 e to the 2x. And then what does this imply? This implies that we can write, so this is a valid individual solution. So then the general solution can also be written as, so y of x is equal to, and I'm going to give tildes to these constants. So this is going to be c1 tilde times e to the 2x plus c2 tilde e to the minus 2x and then minus x over 2 plus 7 e to the 2x. So this looks different from the previous solution. The difference is this term 7 e to the 2x, but we can combine it with the first term, with the c1 tilde e to the 2x. And then from these two terms together, we just get c1 tilde plus 7 times e to the 2x. So c1 tilde plus 7 is just another constant. So it turns out that choosing another particular solution doesn't actually make any difference in theory. In practice, it does, because there is usually one particular solution that's easiest to compute, and all the other ones are more complicated than that. So in our case, this is going to be the solution that's easiest to compute. All right, so now I guess we have 5 more minutes. Maybe let's do one more example. Do you want to suggest an example, or do you want me to suggest an example? Let me suggest an example. So right, let's go back to the whiteboard. So let's try to solve, maybe let's try to solve a third order equation. X triple prime minus 8x is equal to, let's say, 7t. So here x is a function of t. X depends on t. So what do we know from the general theory? We actually know, even without doing any computation, that we can always write any solution in the form x of t is equal to, say, c1 f1 of x plus c2 f2 of x plus c3 f3 of x so this would be a basis made of three functions f1 f2 f3 for the associated linear equation, and then it should be plus another function, let's call it g of x, which would be a particular solution of the equation. So we know that every solution is in this form. And now the question is, what are f1, f2, and f3, and g? And we can compute them. In this case, so in this case, f1, f2, f3 are going to be somewhat more complicated, but g is equal to minus 70 over 8. So in any case, this is what the general theory of linear equations tells us. Maybe we can also say f1 is equal to e to the 2t f2 is going to be some combination of exponential and cosines. So it's e to the power t times cosine of square root of 3 times t. And f3 is e to the t times sine of square root of 3 times t. So in general, this applies to any linear ordinary differential equation, except that in general, the basis is not as easy to find. It's not as straightforward to find. So these are the three basis functions, and in a general situation, they are definitely not as easy to find. Okay, so thank you for your attention, and we'll continue next time with a different topic probably. I think we're going to move on to Bernoulli type equations. Do you have any questions up to here? If not, thank you for your attention, and I'm going to close this meeting. Thank you.
Thank you, Professor. Have a good day.
Thank you. You as well.